Happy Friday. I'm gonna pick up where we left off, right? We just did contour maps. So finding domain. Remember, domain is now a set of ordered pairs. So we need a set of ordered pairs XY that can be plugged in for f of XY. Well, there's no logs, so we don't have to worry about that. There's no trig. All we have is square roots. What has to be true for square roots?
Can't be a negative.
It has to be non-negative, right? So there's a domain. And this one's simple. Equation of a sphere centered at 10, 10, 4 with radius 9. Right? Of course, we can expand that out. Good. 216. 216 minus 81. 30. 135. Domain and range. So set of all ordered pairs x, y such that again we have a square root. What's under the square root has to be non-negative. Right, so what's under the square root has to be greater than or equal to 0. So again, is our domain set of all ordered pairs x, y, such that x squared plus y squared is less than or equal to 4. This domain is easier to visualize. That's a closed disk of radius 2. Right? Closed simply means that the border, the boundary points are all included. Right? Open would mean that the boundary points are not included. For the range, right? The question is, what are the possible values that you can get out of this? Rewrite it. Well, we know all the values we can have for x squared plus y squared. 0 to 4, right? It's obvious that it's going to be not negative. So if this whole thing is 0, we get what? 8 minus root 4, which is 6. That whole thing is 4. We just get 8 minus root 0, 8. Now, if this is between 0 and 4, are you going to get values outside of 6 to 8? Right, that's the question. You're not, are you? As this increases, 4 minus it will start to get smaller. Right? Square root of something that keeps getting smaller just keeps getting smaller, right? So clearly 8's going to be the largest. And it's never going to fall below 0 because it's a square root. And 6 will be the smallest. Range is 6 to 8. Remember, range is still an interval, right? Because range is measuring output, which is a single variable, z, right? So that's still one-dimensional. It's only the domain that'll change dimensions. So this is where things get a little bit harder. We're familiar with the notion of a limit from Calc 1, right? The formal definition of a limit. In English,
We're supposed to know what all that means. Like, what is that symbol with the V and line to? And
that's an upside down A, that means for all. Backwards Z is there exists. Other one is such that.
the one that looks like a ladle next to the E. Yeah,
That you should know.
should. What is?
That's the lowercase Greek delta. Because they should have taught you this definition in Calc 1. It's required. Just a Greek letter.
Okay.
Okay. In English, what this means is we can make f of x arbitrarily close to L by choosing x to be sufficiently close to A. Right, that gives you the ideas of the epsilon and delta bands. This is known as an epsilon delta definition. Specifically, it's the epsilon delta definition of a limit. Okay. First time looking at it, yeah, you're kind of completely lost. But when you actually sit there and look at it, it makes perfect sense. It's actually not that difficult. That's for single variant. For two variant, we no longer have a delta. We have what's known as a delta disk. Hoping I could remember what it was off the top of my head. Oops, open, so it's not less than or equal to, it's just less than. Delta disk centered at a point is just an open disk of radius delta centered at that point. Okay, if you take the limit of a two-variate function, you're going to get a value. It's going to be some number, or possibly not exist. For all epsilon greater than 0, there exists a delta greater than 0. They have the definition of the square root. Such that the absolute value of f of xy minus L is less than epsilon whenever that square root is less than delta. Again, in other words, the limit is L if we can make the function arbitrarily close to the value L by choosing a point xy sufficiently close to AB. Guess what? If it's a three-variate function, it's no longer a delta disk, it's a delta ball. Because now you have that z component. And then the definition will look similar. Going to four-variate, you're now dealing with a delta hyperball, right? A four-dimensional ball. And then the definition would look similar. Right? You can just keep going for the number of variables you have. But even something as simple as increasing the number of variables by one from single variate to two variate makes the limit much harder. Right? Calc 1. You're dealing with just x, right? Let's say that is the point P that x is approaching. How many ways can you approach it? Just two ways, right? You're either coming in from the left of the point or from the right of the point. The limit exists if and only if the limit is the same from both directions. Now we have a two-variate function. How many ways can xy approach P? Four? What are the four directions?
Not sure.
What would be the two directions?
Just select one, right?
You're saying those are the only ways to approach that point? There's an infinite number of ways to approach this point. You have the four cardinal directions, up, down, left, right. Then you have all the diagonals, right? Then you have all those diagonals, and all those diagonals. Oh, but in order to say it has to be a straight line either. You can also approach this point along some convoluted path. Right, I could do something like this. Like, yeah, there we go. That's a way to approach the point. The limit exists if and only if the limit is the same no matter how you approach the point. So that's where it gets more difficult. You still start the same way. Just plug in the point and see what you get. This time, though, if you get indeterminate, simple algebra may not be enough. Right? Because indeterminate could mean the limit exists or possibly not. To show that the limit doesn't exist, Calc 1 was easy. You just calculated the left-hand limit, right-hand limit, and showed that they were not the same. We're now dealing with multivariate. You have to find two paths approaching the point where the limits are not the same. Very common mistake I see is students will show two paths where the limits are the same and go, ha, the limit exists. That's not how this works. Because all you did was said, oh, it's the same for those two paths. But what about the infinite number of other paths that you can approach it? You haven't showed that it's the same. And that's just two variant. What if you're taking a three variant limit? Now your point's in space. Well, if 2 dimensions has an infinite number of ways of approaching the point, 3 dimensions also has an infinite number of ways of approaching. But now you have a third dimension to add in as well. So it's actually a larger infinity. Yeah, limits are not as easy anymore. You have also lost one of your favorite methods of evaluating limits. You've lost L'Hopital's rule. L'Hopital's rule only works for single variate. How do you take a derivative of a multivariate? Can't. It's called partial derivative. So you've now lost L'Hopital. The other methods still work. Squeeze theorem, composite function theorem still works. The idea that if you can find a function that agrees, so a function g that agrees with f everywhere except at the point that you're approaching, then the limits are the same. That still works. But while we've lost L'Hopital, we have gained an important new tool. We have different coordinate systems we can work in now. We can actually convert our limit into a different coordinate system. So for 2-variant, we could convert it to a polar limit instead of a rectangular limit. Doing so, by the way, might actually get you single variant, which will let you use L'Hopital's rule again.
That just something you could do, like, whatever for any reason, there's no restrictions on it, you can just convert them.
You can just convert it whenever you want. You just have to be careful because you also have to convert the point that you're approaching. And it might not be helpful all the time to convert it. It might actually make it worse. So evaluate the limit or state why it does not exist. Well, this function is a polynomial, right? It's a 2-variant polynomial function. Domain of 2-variant polynomial is the entire real plane, R2, which means it's continuous at the point 3, 2, so we can just plug in the point. Two to the fifth, 32. 32 times 3 is 96. Nine times 4, 36. 36 times 7. 7 times 30 is 210. 7 times 6 is 42, so 252. And then 96 minus 252, negative 156. So x, obviously continuous over the entire real plane. Cosine of x minus y over 4. Well, that x minus y over 4 isn't going to change the domain of cosine at all. Cosine is also continuous over the entire real plane. That means that x times this cosine is continuous over the entire real plane, so we can just plug in the point. Because it'll be continuous at pi 0. Cosine of pi over 4. Cosine of pi over 4. Our limit is root 2 over 2 pi. Domain of x squared over x squared plus y squared is the entire real plane except the origin. Oh, but we're approaching the origin. That's a problem. In fact, if you were to plug the point in, you get 0 over 0, which is indeterminate. That means either the limit exists, it could exist, or it could not exist. Your job is to figure out which one it is. Because that dictates how you proceed. If you think the limit exists, you need to try and simplify this so that you can evaluate the limit. If you don't think it exists, you need to find two paths where the limits are different. So, what do we think? Does this limit exist or not? It was very subtle, but I saw both of you shake your heads. That means your job is to find me two paths where the limit's not the same. It also wants to go along with the limit not existing. No, that means everyone else thinks the limit exists. That means the rest of you have to try and evaluate the limit. Have fun. I'll wait. This limit does not exist. That's definitely not spelled right. Okay, why am I having a brain fart on arbitrary? That's right. Let's pick an arbitrary line of the form y equals mx and approach the origin along that path. Well, what's going to happen is this is going to become a single variate limit now. Right? As y approaches 0, x also has to approach 0, so we're fine. We can now write this as the limit as just x approaching 0. Right? Because we're going to eliminate y. Replace y with mx. Yeah, so why don't we replace that one? Oh dear. Easy fix. Notice what we get for the limit. One over 1 plus m squared. The value of our limit depends on the line that we choose. If we choose a different slope, we're going to get a different limit. So in fact, we're going to get a different limit for every single line of the form y equals mx. So I did more than just find two paths where they're not the same. I found an infinite number of paths where they're not the same. So the limit does not exist.
So you chose to like use y to the mx because if surmise that from what you know about the problem already, we're gonna have to figure out.
I already knew that.
Right, so we're gonna have to figure out stuff.
If you're approaching the origin, a good place to start is try along the x-axis and along the y-axis. That will generally get you different answers if the limit does not exist. If they give you the same and you're still convinced it doesn't exist, then try an arbitrary line y equals mx. But that's if it's approaching the origin.
Just a little bit confused. Can you say again why the limit does not exist?
Depends on the line. Right? So for instance, if you choose the line y equals x, that's a slope of 1, isn't it? So the limit would be 1/2. But what if you choose the line y equals 2x? Now you have a slope of 2. The limit's 1/5. They're not the same. So the limit can't exist. You found two paths where the limits are different. That's all it takes.
Okay, so if they were the same,
Then you'd have to keep going. Right. So again, if I would have found that this doesn't depend on the line, that doesn't mean the limit exists. It just means that every line, you get the same limit. You have to show for it to exist that no matter what path you take, and there's an infinite number of them, you get the same limit. Right. So your objective when trying to show does not exist is to find at least two paths where they're not the same. And what about the limit as we approach the origin of xy over the square root of x squared plus y squared? Again, at the origin, this function is not continuous. You can't just plug in a value. In fact, if you plug in the origin, you again get 0, 0. If you would have gotten something over 0, obviously limit does not exist. Right? It's infinite. But 0, 0 means indeterminate. So again, you have to decide, do you think the limit exists or not? Because that dictates how we move forward. Again, we have a very powerful tool at our disposal. We have the polar coordinate system. As XY approaches the origin, what does R theta do? All right, so just think of each piece individually. As XY approaches 0, 0, what is R doing? To what? R is approaching 0. What about theta? Right, but it's got to change to something. I would argue that theta just approaches zero, doesn't it? It's the origin. Origin doesn't make an angle with respect to the x-axis. What do you mean, what was the point?
Fine if we read it in polar coordinates, if it's just the same.
I'm not done yet. I'm just now saying, what is the polar point approaching? Right, so the polar point happens to approach the polar origin. That limit's zero. Mm. They'd have to approach zero. Right? No, I don't think theta actually does have to approach zero. If you travel along that line, theta's not approaching zero. Theta stays constant. Now, the argument here is, doesn't matter what theta does, it still approaches zero, so it's independent of path. Like, so if you tried the same argument here, you get 1. And the limit's not 1, the limit does not exist. Versus if you just say theta is whatever, this limit will wind up being cosine squared of theta, which means it does depend on the angle, so it's dependent on the path.
You know to use the polar coordinates instead of y equals mx. And how do you recognize to do that?
Something because saw square root of x squared plus y squared there and saw that that's r. I mean, technically it's a right-handed limit for r, right? But that's implied because r can't be negative. Yeah, okay, verified. Theta is theta's going to be whatever. So it's just r approaches 0 if we approach the origin. Like I said, not as easy in multivariates as it is in single variant. And by the way, this would have been a case where if we converted to polar, and got it strictly as r, then L'Hopital's rule would now apply because it'd be a single variant limit. Right? As in this case. Convert to polar, now you get a function strictly of r, so L'Hopital's would apply. But do not forget the squeeze theorem. Squeeze theorem is also extremely useful. It's also the technique that's most often forgotten. Everyone always forgets about squeeze theorem. Any questions? Okay. There is not one surefire method for multivariate limits once you get indeterminate. Right? Again, unlike in Calc 1, where you basically have surefire method if you got indeterminate, you knew what to do. Doesn't work like that anymore. The only way to get really comfortable with multivariate limits is to just do enough of them until you start to see certain patterns arise, like when to use polar, when to just try an arbitrary line y equals mx, Right, but as with single variable, just try direct substitution first. Because that could get you an answer, like it did in the first two problems we looked at. And then you don't have to worry about it, right? Oh, I'm done. Here's the answer. There are some limits that you can also still use algebra on. For instance, x squared minus y squared is a difference of squares. It simplifies to x plus y times x minus y. So if you do the limit as xy approaches 0, 0 of x squared minus y squared over x minus y, you can simplify that. And you get a limit of 0. Time I left the bloody quiz sitting on my desk at home. I think this is 11th. No, nope, that's definitely not it. Okay. So it is the 10th. Yeah, there we go. So go ahead and evaluate that limit or explain why it does not exist. Can. It's not what you meant to ask me, though.